Hello, my name is Jendrik Seipp and I'm presenting joint work with Samuel von Allmen and Malte Helmert. In a nutshell, our paper is about optimal classical planning. We're using an A-star search with an abstraction heuristic to find optimal plans. More precisely, we use Counterexample-Guided Cartesian abstraction refinement to obtain the abstraction. And there the bottleneck is we have to repeatedly find shortest paths in the abstraction. And by using an incremental search instead of starting from scratch all the time, we obtain 1000-fold speed up. So how does counterexample-guided abstraction refinement work? Here's the pseudocode for the algorithm. We start with an initial abstraction, and then until we hit a time or memory limit, we find the shortest path in the abstraction. And if there is no such path, we know that the problem is unsolvable. Otherwise, we find a flaw in the path by tracing the abstract solution in the concrete transition system. And if there is no flaw, we know that we found a plan that works in the real transition system. Otherwise, we refine the abstraction for the given flaw such that the flaw cannot occur in the next round again. And when we are done, when we hit the time and memory limit, we can use the abstraction in an A-star search. So to see an example for how the CEGAR algorithm works, we have a small logistics example here where we have one package and one truck, and we have two locations, A and B. And the goal is to move the package from A to B in one of these two goal states. We can load the package, we can unload the package, and we can drive between the two locations. So the CEGAR algorithm would work as follows for this task. So in the beginning, we only have a single abstract state, and all the actions are self-loops in this state. Then we find an abstract solution, which is to do nothing here because this single state is already a goal state. And we check this solution for the concrete task. And doing nothing doesn't solve the problem because the package is not at location B. So we need to distinguish at least between these two situations, which is why we split this state into two states. Here the package is at its destination and here it isn't. And then we repeat. We find a solution which is to unload the package in B. And this solution fails in the concrete world because the package is not in the truck and the truck is not at location B. So we can split either on the truck or the package, and we choose to split on the package again, which yields this abstract transition system. And let's imagine that we hit a time limit now, and then we can use this abstraction in an A-star search. For finding the abstract solutions in the abstraction, we can use any optimal search algorithm. For example, we can use Dijkstra's algorithm, but we can actually use A-star search because we know some lower bounds of the states that were on optimal solutions in earlier iterations. But even if we use A-star search, searching such huge graphs can be a bottleneck, and usually is. And what makes things even worse is that the time for finding a solution grows with the number of iterations because the abstraction grows larger and larger. So the solution to this that we present in this paper is to use incremental search. So instead of starting from scratch all the time, we try to repair the last known solution, and this drastically speeds up everything. Incremental search is also known as the dynamic shortest path problem, and the algorithms for this problem differ in how many transformations of the transition system they support. So some support only adding transitions, some support removing transitions, some support both. Likewise for increasing and decreasing weights of the transitions. And they usually assume a fixed set of states. And obviously this is not given in our case because in each iteration of the CEGAR refinement loop, one state is added. So how can we use this incremental search anyway for CEGAR? We do so by treating the refinement step in the CEGAR loop as two separate steps conceptually. So when we split this state V into two states V1 and V2, all we need to do in reality is to rewire all incoming and outgoing transitions of V for V1 and V2. But if we do a separate step first, so if we copy V into V1 and V2 and copy all transitions, then we don't change any goal distances for U2 or U1, and then we can remove all the spurious transitions. And in this way, we only have to consider the case where we remove transitions, and we can treat this case as the two states already existing. And this allows us to use the increase procedure by Frigioni et al., which is one instance of an incremental search algorithm. And it allows to increase weights dynamically and to remove transitions. So exactly the things that we need. And it works on the shortest path tree. So for each state, it stores which state comes next in the shortest path for the first state. And the algorithm works by first finding out the adjacent states for all the transitions that were changed. And then we move up the shortest path tree and try to reconnect some of the states for which the shortest path no longer works to other states for which it still works. And for all the states where we can't do this, we mark them dirty. And then we run a modified Dijkstra only on the dirty states. And when we do this, we obtain a drastic speedup. So these are the times for finding shortest paths when we refine 100,000 times. And we see that the search times for A star compared to the ones for incremental search are much higher. So here, for example, these tasks, here the incremental version is 1,000 times faster than the A star version. And this directly translates to more solved tasks. So here we see how many tasks the two versions solve over time. And the A star version usually hits the time limit of 1,000 seconds, and then it uses the quick A star search to find solutions. And in contrast, the incremental version has a higher coverage than the A star version, and it almost never hits the time limit. So in summary, we saw that the main bottleneck for this CEGAR approach is to find shortest paths in the abstractions. But if we cast this as a dynamic shortest path problem, we obtain drastic speedups. Thank you for listening.